Okay. Hi, everybody.
So there's a question already whether your slides are already posted somewhere. Are they on GitHub?
Sorry, I forgot to post the slides. Yes. The slides are now posted on GitHub. Thanks for pointing that out.
I'll send the link in just a minute.
Sorry?
I'll put the link for everybody.
Yeah. Okay, hi everybody. Welcome to lecture 4 of 6S083 18S190. So, problem set 2 is just came out last night or early this morning, and it's all about the problem that we started looking at last time on Wednesday, which is how long does it take to recover from an infection if we assume that at each step, in other words, on each day, we have an equal probability P, some probability P of recovery. So I decided to just not discuss that anymore in the lectures and just sort of, make some nice homework questions so that you can work through that on your own. But of course, if you have questions, do ask. So, questions were...
Can you could be somewhat louder or closer to a microphone or something?
Oh.
You're kind of soft.
Okay.
It's not terrible, but I think I've heard you louder and clearer.
Is that better?
Say a few more words.
Is that any better? Can you hear me? Hello?
Maybe a little bit. I'm not sure. Maybe the same.
Strange. Okay. I'll try and speak louder. So, okay. So, yeah. So, we're talking about how long does it take to recover? So that's basically the question. If you have probability P at each time step, how long do you actually take to recover? So you'll work that out in the problem set. So today, okay, so basically, so last time we introduced, we started looking at random models. So we looked at what randomness means really, and how to generate random numbers on the computer. And we just, and then once we've generated some randomness, we looked at, we said, okay, so we have these things called random variables, which are in our context, there's some function which returns different values each time you run it, modeling some stochastic process in nature, some random process that sort of calculates, how long does a light bulb last, or how long does it take to recover? Then every time you sort of run the process, or every time you ask a different person how long they took to recover, you'll get a different answer. But those answers will be distributed in some way. So you'll have some that are more common, some that are less common. And so that's what's described by the probability distribution of this random variable. And so we saw that, well, we can count the different values that come out if we have a discrete random variable that only takes on a certain finite number of values, or discrete values, so not continuous values. And we can count how often each one comes out. That's called the frequency. And then we can divide that by the total number of times we ran the experiment, and that gives us relative frequencies, which are basically what we think of as probabilities. Okay, so that was what we were doing last time. And now, so what are we actually trying to do? So where we're heading is that we've got these random models. We know how we can model recovery. What do we actually want? We actually want some we actually want some model of this epidemic process where we can really talk about actually individuals moving around in space and interacting in some way. So getting individuals coming into contact, whatever contact means, and that's actually one of the most difficult things to model. And when they come into contact, they might transmit the disease. So we are going to, for problem set 3, which will be next week, you're actually going to write a model that does exactly this. And so we're building up all the pieces of that. And so the piece that we're going to build up today is, how do these people actually move around in space? So instead of the word people, We often use the word agents. I believe this comes from economics, this word originally, but now it's used for all these kind of models of social behavior where you have people or companies or something that have some behavior that they individually have some behavior, and then when there are different agents together, they can interact with each other and actually modify their behavior based on the other person. So this is what you might call a complex adaptive system. So the goal of today is just to think about how do these agents move around? How can we model that? And we'll introduce the world's simplest model of motion, or not quite the simplest. The simplest would be they just move in a straight line, right? And so you can use that model. So some of the models that people have been publishing online have sort of balls that are moving in a straight line, and then they collide. When they meet, they collide and they bounce off each other. That's another simple model, it's a billiard ball model. But we're going to introduce a simpler model, at least a simpler to program. So that's that's the idea. So today we're just going to look at this motion in space, and then we'll build up all the pieces so that next week you can actually start writing this simulation where we'll actually see an epidemic outbreak in a population moving in space. Okay. So we'll introduce this idea of what's called a random walk. It's a model of literally random motion in space. And we'll also look at how to characterize the variability of a probability distribution. Okay, so let's look at random walks. So as I mentioned last time, there's this concept of Brownian motion. We even saw a video that sort of represents it. And Brownian motion is important in many Brownian motion, which means this random motion of an object in water is moving around just because it's being kicked by the water molecules is fundamental in many areas. So in biology, you might be interested in how a protein moves inside a cell. In engineering, you have the noise of a jet plane, which actually we don't hear very much of right now, but usually it's a problem, etc. So it's in many areas this is a key concept. And as we saw, well, you could simulate many particles all bouncing off each other, but that's going to be computationally expensive to do, and it's actually just going to result anyway in some kind of motion where this particle moves around seemingly at random. And so instead of doing that complicated thing, we'll do something much easier. We'll just sort of simulate this idea that we have these random kicks, right? So what does that mean? We have some particle that we're thinking of being big, and then it's immersed in a sea of smaller particles that are the water molecules, say, and those molecules are moving around, and they just sort of collide with this big particle and bounce off it. And when they bounce off it, they'll move it a little bit in the opposite direction. Or they'll move it a little bit in the direction they're going, but just a tiny bit because it's heavier than they are. And so the effect of a sequence of these these collisions will be that this thing starts, if I draw where its center point is, just like I did in my simulation the other day, you'll see that it sort of does this apparently random motion. That's the point. And so instead of simulating all of these complicated behavior, actually, let's just make that a different color. It does this, this is the trajectory of it. It's the trajectory, it's the center of this particle sort of moves around in some random way, in a very wiggly way, because it's constantly being buffeted, being kicked by all these water molecules from all sides at once. And so it sort of gradually shifts its position around in some random way. We want to be able to simulate that without simulating actually all of these molecules moving around and colliding with each other. So the way we'll do that is we'll just say, okay, this particle is actually going to move literally at random. So the simplest possible model of that, we're just simplifying everything as much as we can, as we discussed in a previous lecture. Start with the simplest model, then make it more complicated later once you understand what's going on. So the simplest model is this. So we're going to be on a line, and we're going to put we're just going to have points that are the integers on this line. That's the only position that we can be in, any integer point, any whole number. We're going to start at 0, and then we're going to move by jumping to a neighboring point. So either going to jump left to -1 or right to 1 at the first step. And then at the next step, wherever you are, it's going to carry on jumping from there. So if we arrived at -1, then we could go left to -2 or right back to 0 at the second step. So this is like step 1. This is step 2. If it arrived at -1, then it can carry on. So that's a simple model of this random motion. So we're going to have jumps. And it's going to jump a distance plus or -1, and those happen at at each time step. So we're going to have discrete space and discrete time. So you could say, well, a protein does not live on a lattice. So this is this is called a one-dimensional lattice or grid. The protein doesn't live on a grid, but so if I make the mesh, the size of the distance between these grid points small enough, then it will look like from a bit further away, if you sort of blur your eyes, it will look like it's moving in a continuous way. And similarly, the jumps could be, you could argue that a protein does not jump. It actually moves in a continuous way. So you can add all of this later, but this is the simplest thing we can do. Okay, so that's what we're going to do. So then the question is, okay, so now we want to actually just immediately go. Of course, if you go to a probability course, you have probably already seen this, and you can do a lot of analysis mathematically of this model, and you can prove a lot of things about how it behaves. But we're going to ignore all of that and pretend that we don't actually know any of that, and work it out using the computer as an example of computational thinking instead. Of course, in reality, you want to combine those two approaches. If you can do things mathematically, then that gives us information that's often more complete than what we can get from a computer simulation. But often, as soon as you tweak, how this, for example, I'm not going to jump plus or -1 with uniform probability. I'm going to have some complicated distribution of how I jump. Then suddenly you can't really do very much mathematically often. So, okay, so we have to just learn how to do this on the computer. So how can we actually generate jumps of plus or -1 on the computer? So uniform here means that they have the same probability. That means I'm going to jump left with probability 1/2 and right with probability 1/2. So again, you could stay at home, you could stay where you are, with probability 1, like we're doing right now. With certainty, you could stay at home, or sort of almost certainly you could stay at home. But we're going to say that you can't stay at home. You have to jump every step. That's, again, the simplest thing you could do. Simplest to program. Okay. And you could also make these not equal, right? You could say I want to jump left with more probability. So then that will give completely pretty different answers, different results. Okay, so how can we actually do this in Julia on the computer? So sorry, that shouldn't be there. So one possibility, so we know we've already seen this rand function that generates random numbers, but it turns out that it's much more flexible than it seemed. So we used it just to generate random numbers between 0 and 1, any real number between 0 and 1 or floating point number. But actually you can use it to choose random things from some collection of objects. So here we're using a new concept that we haven't really seen yet, which is called a tuple. This is called a tuple or tuple or pair, ordered pair. So it's the same as the mathematical concept. It's written, with brackets, with parentheses, and it is written with a comma separating two values. And it literally means the ordered pair -1 followed by +1. And so I can do rand of that object, and it will actually choose one of those objects inside this container, and it'll choose them with uniform probabilities, or with equal probability, it'll choose one of them. That's one way to do it. And that will directly give us a -1 or a +1. A different way would be to say, okay, I can actually generate a random Boolean number. So remember that a Boolean is true or false. a Boolean variable is true or false, and I'm actually using the name of the type, which is bool with a capital B. And now I want a random one of those. So again, true or false, that's a finite collection. And so when I take rand of it, it's going to choose one of those values equal probability, so with probability of half. Okay, so when I do that, I'll get out the value true or false. And now what I'm saying is I want to convert that. I actually want a number out, right? I want -1 or +1. But when I convert that true or false to an integer, I'll get a 0 or a 1. So 0 corresponds to false, and a 1 corresponds to true when you convert it to an integer. So how can I actually now convert that to -1 or 1? So of course I could do that with an if by saying, oh, well, if the result was 0, then give me a -1. Else, if it was a 1, give me a 1. I could do that, but maybe there's a different way to do it. So we'll come back and actually do it in Julia in a minute. So once we've got one of these jumps, okay, so yeah, and also this syntax, I don't think we've talked about it here. This is a new way in Julia of defining a function that I don't think was mentioned. This defines a function, just like the word function does, but it defines a sort of function which is short, a short function, so it fits on one line. It's just a nice syntax that's very much basically the same as the mathematical syntax for defining a function. You just give the function name and parentheses and whatever parameters you want to put inside it, and you can put parameters inside the parentheses, and it's just like a mathematical function, right? So I could do something like f of x equals 2x. That's a valid piece of code in Julia, which will define a function called f. It takes one argument x and returns 2x, just like as if I were doing it in a mathematics book. Okay, so once we know how to do a jump, and I'll come back to that in a minute, now we want to do a random walk. So what is that? It's just a sequence of random jumps, one after the other, as I said, right? So we start somewhere and we jump somewhere, then somewhere else, and somewhere else, and somewhere else, and somewhere else, and we sort of meander around the world, randomly coming backwards and forwards, you know, going left, then right at random. And so after a time, after a number of steps, a certain number of steps, say n, I might be back where I started, or I might be quite far to the left, I might be quite far to the right. So we want to know, well, how likely is each of those things? So if you think about this as the motion of some kind of animal, then the animal starts from its nest, say, and is sort of exploring the land around its nest. And then at some point, of course, animals don't behave exactly like this because they'll come back to the nest at some point to roost, to sleep, basically, or whatever. And so that's a more complicated process. And actually, maybe that's a more realistic model of motion for a human, right? So a human has a house and they'll go and wander around in the world, which probably isn't random either. But there's actual data you can get now, or at least there's data around. I don't know how easy it is to get. Usually the hard thing is getting the data, of course. There was a nice talk the other day about this data about movements of people in Boston and New York. And so you can, of course, the motion is not random. They're going to work, and then they're going to the shop, and then they're coming home. But you can model it as this random motion, but you would have to include this sort of idea that they're being attracted back to where they live. And that's probably a good thing to add to the model later on, once you've already started with the simplest model, as I keep insisting. Okay, so let's actually go and do some Julia. So yeah, we are monitoring the chat. I'm not monitoring the chat, but Alan is monitoring the chat. So do ask questions, and then I can answer them as we're going along. And I shared the wrong thing, sorry. It's confusing. Okay, can you see my desktop? Can you see the notebook?
Oh, we see everything. Good if you could zoom in a little bit. You know the usual tricks.
Okay, so So let's define this jump function. So we did rand of -1 and +1 as a tuple. Okay, and this will actually define a function just as if I'd written instead function jump. It doesn't take any parameters, right? But I still have to put the parentheses there. And so this is an alternative. This is exactly the same. That's like a short function definition. So we're doing random walks. Short function definition. One-liner. And this is exactly the same. Return rand of -1 and +1. Now, what we've seen so far, and so if I try and run that function, what happens? Well, if I just put the function name and I forget to put the parentheses, as usual, it will just tell me. Unhelpfully, you might think that that is the name of the function. It's actually very helpful because it also tells you how many methods it has. But when I actually put the parentheses in, it will run the code and will generate this random number. And if I use Control-Enter to run it again and again, I'll see that it's randomly jumping left -1 or right +1. So those are two equally valid ways of writing the code. Now, until now, we've been using arrays only. So you might think, oh, I could do that with an array instead. Of course, you can do that. It'll do exactly the same thing, but it turns out that that is actually slightly slower, or maybe considerably slower, because arrays have actually a lot of overhead, a lot of sort of extra stuff that they carry around with them because they can change size, whereas tuples are a fixed size. So this tuple knows that it's of length 2. For example, if I call that t for tuple, -1 +1, and I ask what is the type of t, it tells me, oh, it's a tuple. And look, it knows it contains exactly 2 integers. So this curly brace means that this is a type that's parameterized with these 2 types inside. So it's basically, you can think of it as a tuple of int and int. It knows that there are exactly 2 of them. And by the way, also tuples cannot be mutated, cannot be modified. If I try and modify it, it tells me that's an error. And that's to do with efficiency as well. Efficiency is speed. So basically using tuples when you know exactly what size your object is usually much more efficient. Okay, and by the way, we had this discussion last time about this, the newly random variable. So that was if my random number is less than p, then return true. Alan pointed out that my code was far too complicated, which it was. And so this is the simplest version you can have. So Bernoulli of p as a one-line function definition is just going to be, I generate a random number by calling the rand function. So I need my empty parentheses. And then I check, is that less than p? And that comparison again will give me a result. And that's the result I want to return from the function. So that is the shortest definition possible of this Bernoulli function. Bernoulli of 0.25 will give me, every time I run it, will give me a different value. That's a nice, this is an example of how Julia enables me to write sort of really concise code that is still pretty readable, right? So you might want to put parentheses here if you want to emphasize that I'm evaluating this and then returning the result of that evaluation. But you don't need them. You can just do it like that. Okay, so I think it's pretty nice that you can write code like that, and you end up writing a lot fewer a number of characters that's much less. So you basically the Julia code is often much shorter than code in other languages to do the same thing. Significantly shorter, let's say. Okay, that was just a side remark. So yeah, so we've got this jump. So when we call jump, what does it do? It does that. And so we can call jump a lot of times in the usual way using an array comprehension, jump for I in 1 to 10 inside square brackets will give me this, data, right? So I'm generating data of which way I'm jumping. But that's not all I need for my random walk, right? So now on to random walks. For my random walk, I need to know, well, which position am I at after a certain amount of time? So if I move left and then I move left again, well, now I'm at position -2. And so I need to somehow get that out of this process. So of course, as usual, basically there are always various different ways you can do these things. We're just looking at one possible solution. So, in other languages where you need to think about vectorizing operations, because that's the only way you can get good speed, you would actually, you would call some built-in function to calculate this thing, to add up all of these steps to get the position that we're at. So I don't want to talk about that because that's not what I would usually do in Julia. So what would we usually do in Julia? I would sort of write a function, walk is going to take a length of the walk that I'm interested in, n, and we probably want to, and so it's going to just do n jumps, right? So how do we do that? Well, we're going to do a for loop because we know there are n things. So we're going to write a for loop, and then we're going to jump each time. And what do I want to do with that jump? Well, I want to have some knowledge of which position I'm in, right? So let's call the position x equals 0. It lives on the x-axis, if you like. So it starts at 0, it's an integer. And now at each step, what's going to happen? Well, I'm going to actually take my current position and add whatever I get from this result of this jump function. And that's all. And I return x at the end. And I could write this, by the way, and it's probably better to write it as x plus equals jump, which means there's a shorthand syntax for x equals x plus jump. So actually, let's write it the other way around. We'll actually use x plus equals jump, and that means x equals x plus jump. So when you have a long variable name here, you don't want to be copying that long variable name twice. That's just likely to introduce errors, and it's actually difficult to see that they're the same variable name. Whereas here, I'm actually saying I'm modifying, if you like to think of it that way, updating, let's say, updating this variable by adding the result of this jump function. Okay, so let's try that out. Walk of 10 is supposed to give me the position after 10 steps. And indeed, when I run it a few times, it gives me different positions. And I can never be above 10. Actually, I'm hardly ever, just by running this a few times, you can see, well, in principle, I could do 10 steps all in the same direction. So I might get to 10 occasionally, but actually, and there was an 8 there, but actually, I'm never seeing 10 come out. Why is that? Because it's very unlikely. So that's what we want to characterize. Okay, so probably we don't just want either the final value. At least to start with, we probably want the whole, let's call it the trajectory of the walker. Where does it live at time, where is it reached at time t, time n? So let's call this trajectory. It's a different function. It has, because now we're going to store all the intermediate positions. So I hope that by now you all know how to do that. So how can we maybe have some chat responses about how would we actually store all of these positions in this, store them? Yeah, what would we do to store these positions that I'm generating during the course of this random walk, random motion?
People can't, oh, I guess people can chat.
Yeah. Yeah, so there's vector, yeah. It's just one word, vector, exactly. So we're going to introduce a vector, let's call it x's, just xs. And so how do I define that vector? Does anybody want to chat and put that in the chat? How do I actually, what's the code?
Just to note that the chatter only goes to the panelists and not to everybody. So you'll have to read it, Dave.
Oh, I see. Yeah. Okay, so somebody's saying, so the first response was make a vector, and then the second person said make zeros of n. So that is one possibility. Because we know how many steps we're doing, I could do zeros of n. But suppose what I wanted to do was wait until this random walker reached a distance 10. Then I wouldn't know how many steps that I needed to do. So what could I do instead?
Okay, I'm making it that now. I think everyone could chat with everybody now. Okay,
so somebody's saying x can be initialized as an empty vector and then push the position we're in every time we make a jump. Perfect, yeah. So I could initialize x as an empty vector like this, but it's usually better to give it a value, an initial value. So I'm going to call that x, I'm going to put the initial value of x inside the vector, right? So what's the difference between those things? If I make an empty vector, so whenever you have a question about how does Julia behave, what is the first thing you should do? You should ask Julia, how do you behave, right? So what does Julia do if I define an empty vector just using two square brackets with nothing in between them? It works. It gives me an empty vector. Let's call it v for vector. It works, that's fine. And then I can add stuff to it. If you remember, that's with push bang. I put the name of the vector and then the value that I want to add to it. And now v changed, great. Okay, but you'll notice that it says that v is an array of any, comma 1. That means that I can actually, my vector v can contain anything, any type of object. So for example, I could put a string in there, hello. And now it's a vector that contains the number 10 and the string hello. So sometimes you might want to be able to do this. There are valid use cases when you want to do this, but this is a very bad idea. This is going to be very slow in Julia. Basically, Julia is fast whenever it can work out what is the type of the things inside the array. Why is that? That's because of how it works internally. Basically, if you have something like an egg box, where an egg carton, where you have the exact number, the exact same space for each egg, then if I want to know where is the 10th egg, I can just sort of move up by 10 times the size of one egg and find where it is. But here, I don't know. This string that I put in might be extremely long, right? Hello, hello, hello. So that's using much more space than my integer is using. And so if I then have another integer over here, it doesn't know how far along it needs to go in this array before it reaches this other object. And so it actually has to store this in a different format, which is just sort of boxes with pointers, with arrows that are pointing to some memory somewhere else where the actual objects are stored. This is called boxing. And this is what other languages do that are not fast. And this is exactly what you want to avoid in Julia. So how do I avoid this? I actually make an empty array, but I tell it, oh, I only want to store integers inside. I only want to store things which are of type int64. And then the way we do that is by just writing the type name in front of the square brackets. That now gives me an array which only can hold int64. So if I push to that array 10, that works. But if I push string to it, it doesn't work. It's an error because it cannot convert a string into, it knows that it has to try to convert whatever I put into this type that I'm forcing it to have inside. So that seems like a downside, but actually it's what's going to give me good performance. Okay, because it knows exactly where to look to get each element of the array because they're all the same size. Okay, in memory. So sorry, that was a little digression. So yeah, so let's carry on with this trajectory function. So we've initialized this array. So usually what I try to do is try to initialize an array with an element already, with an initial value, right? That will determine the type that's in the array. Determines the type of what's called the element type of the array, which type of thing it can hold, right? So if I do v equals, I don't put the right, so I had to put the name of the type if it was an empty array initially, and sometimes you might have cases where you want an empty array. But in many cases, you have an initial value, and so you just put the initial value inside the square brackets, and that will create your array with that value inside and fix the type of things that can be stored in the array as well at the same time. So that's the way I would usually, that's like the style that I recommend. Okay, so once we've done that, as the person on the chat said, now every time we get a new value of x, I want to add it into that list, and I'm going to do that with push bang x is comma x, the current value of x, right? So basically what's happening is at every step, x is being modified, x is being updated, x isn't just a number. So yeah, right. X is being updated, and I'm just adding it into this array. And then at the end, I'm going to return that whole array. So that's my new function trajectory. So now let's run that, with 10 steps. And what do we see? Now we see that this walker is moving around, right? So it's moving left and then left and then left and then right and then left and then left. So I'm seeing that, but I'm actually seeing where it ended up as well. So that is my, that is a function that will do this random walk in space in one dimension. Okay. So what would we like to do with that function now? Can we maybe have some chat ideas? What's the first thing that it occurs to you to do with this data?
And it's okay to send chats now to all attendees, I believe.
Okay.
So you might want to do that. Maybe it's more fun that way.
Yeah.
Okay, we got one answer.
Plot it. Yes, fantastic. That is the first thing that the first instinct that you should always have, in my opinion, is I have some data. It's difficult to, okay, here I have 10 values, I can sort of understand what's going on, but now if I put 100 values, well, it's really hard to see what's going on, right? So I don't want to do that. So let's plot it. So let's call this something. So just traj equals trajectory, right? I'm very bad at inventing good names, but you should practice inventing good names. So traj, I'm going to plot it, right? So if I do plot of traj, what happens? I get an error. Why? So yeah, I actually quite like this interactivity, but
it's much more fun for everybody.
Why do I get an
Why?
error?
We're asking. There we
using
go.
plots. Yes, thank you. I need to type using plots to load in a plotting library, and because the plot command is defined inside that library, and remember that I need to load this library every time I use Julia, every session. I need to load the library. I do not need to install it, right? I don't need the package add because I already did that sometime in my life. It's just on my machine, and using plots will load it from my machine. Everything's local. There's no internet access here. So the only time you need internet is when you're installing the package the very first time. Okay, so I'm going to just use the plot command, plot traj. And so as usual, it will use 1 to n as the x-axis, where n is the length of this object. And as usual, the first time I do a plot, it takes a few seconds. And then hopefully we can get a beautiful plot. And it looks like that, right? So what do we see? So we're seeing the trajectory of this random walker moving around. So probably we want to add dots just to emphasize that actually, okay, those lines are not real, right? The walker is jumping. It jumps instantaneously from this position to this position at the next time step. So really, its position is sort of a step function. It's constant here, and then it jumps suddenly up to here, and then it's constant, and it jumps suddenly up. So we could draw that. It's just a bit more annoying to draw it, so let's not bother right now. And so this is just, visually, maybe it's slightly easier to understand like this. Okay, so also we probably want to know where 0 is, right? So for example, we could ask the question, how long does it take for this walker to return to where it started, to return to 0? So in this particular case, it took something like 30 steps, right? If I run another simulation, let's just do it down here. It took 20 steps. If I run another one, it took, so of course I should actually write some code. Instead of just looking at the picture, I could write some code to say, well, when did it reach 0 again? So, and that's actually a very interesting question, by the way, which has a very surprising answer that maybe we'll talk about at some point. Okay. So that's like, if you're a gambler and you start off with some amount of money, when do you run out of money because the casino is biased against you, right? So yeah, okay. So now what do we want to do? So we've visualized it, but we probably want to add the 0 line is what I wanted to do. So there's a special function to do that in plots called hline bang. It's bang because it's going to add something to the plot, right? Remember the bang functions add to the existing plot. That's what the bang means in the context of this plots package. And what you need is a vector actually of positions where you want the line. So if I do hline bang of the vector containing just 0, it'll do a horizontal line just at 0. If I add 3 as well, then it'll do 2 horizontal lines. But we just want one at 0, and we're going to make it a dashed line, and there we are. It's much more visible now. So of course, I probably want to get rid of the there is a way of changing the size of this thing. I think its size equals 300, 300. Yeah, just to make it a bit more visible. Something like that. Okay, So now what do we want to do? So, each time I ran it, we were getting a very different picture of where this particle is, or person is at time n on this line. So probably what we want to do is run several of these simulations and plot them all on the same graph. Okay? So how do we do that? So you've probably struggled with it in problem set 1. So let's just go over it a bit. So I'm just gonna say I want 10. I want number of trajectories equals 10, right? No magic numbers, please. So I shouldn't do it either. Number for I in 1 to number of trajectories. This I is just a counter. I'm not going to use it. And I'm going to, so I'm going to make an empty plot to start with. And I'm going to call it P, right? This is the name of the plot object, is P. So I'm defining a new variable called P, and it is this complicated thing, which is this plot object. And then every time, what I'm going to do is calculate a new trajectory and plot it. So I'm going to just copy this command, actually, well, so I don't need the plot again. Okay, so I don't, oh, sorry. What happened? Oh, what did I do? I think I lost the,
Did it close or is it just somewhere buried?
I don't know. That's annoying.
You'll have to load plots again and everything.
Yeah. So I need to, yeah, so that's a good learning opportunity. So every time you reload the notebook, it will not know all of these definitions. You have to rerun all the definitions that you care about. So like I have to find where this jump definition is and rerun it. So I could just go cell, run all. That will run all of the cells one after another, starting at the top. Maybe I should just do that. Let's just do that. Okay, so we'll go through one by one and rerun each cell. And as Alan said, in particular, I'll have to reload the plots package, right? So it's going to be again, so basically you should avoid restarting Julia whenever you can avoid it because it just takes a bit of time to load these things. So again, so what's happening is compiling code to machine code, which will then run fast the next time, but it takes a while to compile it the first time. And there's work being done in Julia in the community to make that process much faster. Okay.
Isn't there a bounty, like some very large amount of money to make it faster?
Oh, maybe, yeah, I'm not sure. So I could, do traj equals trajectory of n, where n is the number of steps, let's say, num steps equals 100, num steps, plot traj, don't need the size, let's put the size up here. Let's just size equals 500, 400. And then plot the trajectory. I don't need the points anymore. End. I run it. I'm expecting my beautiful plot. And what happens? I don't see anything. Why is this? Because, as I said, at some point, the for loop does not return anything. For loop does not return anything. So I actually need to just reevaluate this P, this plot object at the end. And when I do that, I visualize the plot. Right? Let's get rid of this legend. So there we are. We're seeing several random walkers in different colors, and they overlap at the start, and then they start diverging. And so now, if I just let's call this number of walkers. Actually, that's more clear. Number of walkers. So if I just do 100, then I start to see something interesting. So the visualization is not that clear because, for example, here I have 100 walkers, but it's not really clear where they are because there are only sort of 20 or 30 different positions where they've arrived at, because there are some in the same place. So what I really want to know is, well, how many are there in each place? But let's just carry on increasing this number a bit, and if your computer's fast enough, you start to see that what's happening is I'm getting this kind of shape. That's a particular shape and that's growing at a certain rate in time, right? So on the x-axis is time, basically, the number of steps. And so how far, so what I have here, because I ran the simulation several times, what you can think of is that I have a cloud of random walkers that are all independent. So they don't see each other, they don't bump into each other because I haven't included that in my model. They just pass through each other. Actually, because we're in one dimension, it's equivalent to thinking of them bouncing off each other. But, oh no, it's not quite true. Anyway, and so what we see is like this cloud of walkers. So imagine if you have a beaker of water and you have some dye, like potassium permanganate or whatever it's called, the pink dye, in a crystal in the middle of this beaker of still water. What's going to happen? The dye will gradually spread out in space. That process is called diffusion, and this is exactly what we've just modeled. So we have a number of dye molecules that only can move in one dimension, and they're gradually spreading out in space. And so the question is, how fast are they spread out? Right, so what could we do? We could, try and work out, oh, well, we could try and calculate the maximum distance. So the way I did it here, I ran each walker separately, right? This function trajectory runs one walker and then runs the next walker and then runs the next walker. So a different way of doing the simulation could have been, well, I have n walkers, and I'm going to do one step for each of the n walkers. Right, so probably I'll leave that for the homework. Okay, so, but as I said, if we have a lot of walkers, then they're just sort of overlapping on top of each other in this picture. So that's kind of not helpful. So what do we actually want to do? We want to see how many walkers are in each different place, right? So, well, I need to actually store some data then. So, here what I did was just, I generated each trajectory and then I plotted it. So there's a record of it on top of the plot, but there is not actually any record of the actual data that I generated anywhere. This is usually a bad idea. Usually what I want to do is generate the data and then plot it. So in particular, probably we would like to make an animation. I like visualization animations. We'd like to make an animation of how does this cloud actually spread in time as I move time along. So then what I need to do is actually generate all of this data and then use it later. So, okay, ideas for how we can do that in the chat. So basically I want to have n walkers. I want them all to be available at once. And then I want to make each of them take a step. Okay, we have a chat comment, and it says pre-compute. Yes. So because we have some randomness in this system, if what you could try and do is you could do this. You could do let's suppose we just want to visualize one random walker moving along. Then what can I do? Well, I would try and manipulate for n, the number of time steps, going from 1 to 20. And then I would make traj be the trajectory up to time n, and then I would just plot traj. So I could do that, and it says at manipulate not defined because I forgot to load the interact package. So I could try and do this, and then I would hope that what I would have would be a trajectory, and I would see how it moves in time. But that's not what I'm going to see. What am I going to see? I'm going to see, if I start at 1, and then I sort of try and move it in time, it's just completely all over the place. It's completely haywire. I'm not seeing the same random walker, right? Why am I not seeing the same random walker? Because this trajectory function recomputes like from scratch every time, and it uses different random numbers. That's not what I want. So as the person said in the chat, as Moises said in the chat, let's pre-compute the data, right? So let's just call traj is the trajectory. So I'm going to pre-compute the data. That means just compute it before you run the visualization. So traj is trajectory of size n, which is going to be 20, say, and then I do the manipulation for I in 1 to n, and I view the trajectory, and I want to plot the trajectory, but how am I going to restrict it to only plot up to time I? So in the chat, please. Yeah, so I index into this vector, so traj is a vector, right? I only want the parts of the vector from the indices from 1 up to I. Okay, so when I do that, I get that this, so by the way, just to remind you that you can do, if you want to fix the initial value of your slider, you can do slider of 1 colon n comma 1 value equals 1. That will initially put it to value equal to the value 1 for the value of the slider. So now, indeed, it is reusing the same data. So I am seeing the same walker moving along, but of course, my visualization is a bit annoying because what I actually need to do is fix the x limits, you know, to be sort of 0 up to 20, 0 up to whatever the final time is, n, and fix the y limits probably to be, you know, something that encompasses the range of this walker that you will only know after the fact, or you could like look at the maximum and minimum of the data. So now I get my nice visualization where I actually see the progress in time of my walker going along, and I can go forwards and backwards because I'm just visualizing the data which I already computed. Okay, so now we want to do that for n walkers all at the same time, right? So how do you suggest, so in the chat, how do you suggest I actually run n walkers all at the same time? No, nobody wants to suggest anything. Q&A. Okay, there's Q&A and there's chat. Oh, is that the same thing?
Not quite the same thing, no.
Very confusing. What's in Q&A? I don't see it.
If you click on the Q&A, you should be able to see it. But there's a question: can we define x limbs and y limbs as the max min of our data?
Yeah, you can do that. Yeah, you can define x. Yeah, so you would do something like x limbs is 0 up to the length of traj, and y limbs is, you know, goes from the minimum of traj to the maximum of traj. Yeah, so there it went from -5 to 2 instead. Yeah, you can certainly do that. Yeah, that's a good idea. Yeah, pre-compute the trajectory for all walkers and then plot each. Yeah, so, okay, so how are we going to compute the trajectory for all of the walkers? Basically, walker 1, or traj 1, if you like, is going to be a trajectory. N, where n is going to be 20. And then, you know, traj number 1 is that. What is going on? Traj number 1 is that, and then traj number 2, I'm just going to copy that, and then traj number 3, I'm just going to copy that again. Oh dear, I seem to be doing a lot of copying and pasting. That sounds like a very bad idea. So there's another suggestion: user 2D array, assign each walker's vector to a row within a matrix. Yeah, so you all have the same idea. That's certainly one possibility, and that's almost what we're going to do. So yeah, so basically copying and pasting is bad. Right, so rule, never copy and paste, except occasionally. So somebody suggested a dictionary. That's also a possibility, but a vector is better if you can use a vector because it's slightly faster, maybe twice as fast. So never copy and paste. Instead, what we should do is what? Automate. So basically, what are we doing here? We're, you know, introducing basically indices into some data structure. So that's why people are suggesting a matrix. But actually, I would say that in this particular case, let's not use a matrix for now. What could we use instead? So what am I doing here? I've got this thing called traj, and I'm indexing with one single number. So actually, what do I have? If I'm indexing with one single number, I have a vector, actually. So, but each of the entries in that vector is a vector. So how does that work? So I'm going to do something like traj is the first trajectory of size n. And then I'm going to push into that vector. So if I just ask Julia, what is that object? Oh, look, it's a vector, it's an array of dimension 1, but inside that array, actually the entries of that array, that vector, the entries of that vector are vectors. So this is a vector of vectors. So I can actually add into that object by push, because it's a vector, and I can just grab another trajectory, generate a new trajectory by calling my function, and then put that into that old vector. And now I have a vector with two vectors inside. Right? And if I ask now, instead of traj1, traj underscore 1, I'll actually say traj index number 1, then I get the first vector out of that array. So you could say, oh, well, this vector of vectors, that is just a matrix. And so you're sort of right. But in Julia, conceptually, of course, that's true. And mathematically, that is the sort of the same object. But actually in Julia, there is a difference. And even, if you're careful, it's even stored in memory in the same way as a matrix would be stored, but it's not the same object. Right? So there is a concept of matrix, of course, in Julia. Which I don't remember if we already saw.
Can I interrupt with a good question from the audience?
Yeah.
So the question is, wait, it looks like you're putting in lots of data. Why aren't we using append? Why are we using a push bang instead of an append bang?
Okay, interesting question.
So that's a good question, right?
Yeah. So let's look at a small example. So yeah. Okay, yeah. So what's the difference? So there's this other function that I have not mentioned yet because I almost never use it, called append bang. So you have to be careful because in some other languages, what in Julia is called push is called append. But in Julia, append is something else that sometimes is called extend. So you just have to be careful. So you can just ask Julia, have we mentioned this help yet? So question mark and the name of a function will give you some help on that function. So push bang, it says insert one or more items in collection, right? So, okay, so here's the example. So let's look at that. So, okay, so this text is quite long, so let's just hide it. But by the way, you can hide a long output by moving to this box where it's gray and clicking some number of times, double clicking, and it'll hide that output. So it's still there. You can double click on it again and to show it, but it's just hidden. Okay, so so the example is 1, 2, 3, and then got a vector 1, 2, 3, and then I push. What happens if I push one element? Well, it adds that one element. What happens if I push two elements? Well, it adds both of those elements, but those were extra arguments of the function. What happens if I try and push the vector 4, 5? Well, what it's going to try and do is add the vector 4, 5 into the array as the next sort of entry of the array of the vector. But this is going to give me an error because we know that we can only store things of type int. Now we're trying to store one object of type vector inside, right? And that's not going to work. But if you have a vector, you might want to add all of the elements that are inside the vector into V. And that's what append does. So append takes this vector and now undoes that vector and gets all the things that are inside out of there and adds them one by one into the array. So that's the difference. Push adds the array adds the vector as a vector. Append adds the elements that are inside the vector into the original vector. Thanks, good question.
Wait, but did you fully answer it? I mean, it looked like you were adding lots of elements, so it looked like you should be appending.
Right, so.
Plus you were, I mean, the whole point is that it was like a vector of vector.
The point is that I actually want to keep the vector, I want to keep each vector intact. I want to keep each vector whole inside my traj vector. This is two vectors. Those are the two elements in my array. It says it's an array with two elements. So if I can add another one with, so basically this trajectory function that I wrote returns, what was it, n? Returns a vector, right?
Do you want to maybe, Dave, you want to hold on a second? Do you want to maybe dissect this?
Sure.
I was hoping you wouldn't hit enter.
All right.
But yeah, I was wondering if you would like to possibly dissect this notation here.
Yeah, I did.
Oh, did I miss you saying that? Okay.
Yeah. This is
All right.
an array of one dimension, and the thing inside the curly braces is the type of object that is stored inside that vector. So an array of one dimension is also called a vector, and inside that vector, Julia tells me what kind of objects I'm allowed to store as the elements of that outside vector. And the answer is, in this case, those elements are of type vector as well. So each element of my outside vector is a vector.
So another question that arose is,
data inside there, it thinks of it as two elements, and each element is a long vector.
so another question that arose is, what about using an array comprehension to build a vector of vectors?
Oh, that's a great idea. Yeah, let's do that. Yeah, so how would I do that? So I'm going to call a trajectory of n, and I'm going to do that 10 times for i in 1 to 10. What does that give me? Indeed, that gives me a vector of vectors. Yeah, that's exactly what I'm going to do. So let's call that walkers, right? Okay, so now we have this vector of vectors, which you might think looks suspiciously like a matrix, and indeed, as I said, it is conceptually, mathematically the same as a matrix, but in Julia, it is not the same as a matrix. And so, nonetheless, what do I want to do now? I want to do something like the following. I want to take where each walker is at the last point in time, right? The end point that each walker got to. And I want to collect those together into, say, a new vector, which is going to be positions at time t, positions at time 20 in this case, or whatever the size of the thing is. What is it? N is 20, I think. Yeah, so positions at time 20. So how am I going to do that? Can you think of a way to extract from each of these vectors the position at time 20? So I'll put any suggestions in the chat as well. And I'm now completely lost sight of where the chat window is. It's just, when you have a full screen, everything just goes completely wrong with Zoom.
We don't have any.
No
answers yet.
So how do I, so let's suppose I have a single trajectory of length n that I generated. How can I extract just the last n element of that? So I could do single traj and index it with n. That will give me the nth value inside that vector. Or I can do single traj and index it with the word end. So it's confusing, the symbol n and the word end. Right? End means give me the end final element of the array. That gives me the same answer. Oh. What? That's not good. What's going on? So the point is that length of single traj is not actually n because I defined it wrong. Okay, that's annoying. Yeah, because it has the first, because it has the final, because it has the initial, because it has the initial position, which is like the position at time 0, and I did n steps. That means I get n plus 1 data points. Okay, so this is not the correct answer. Single traj index n, it should be n plus 1. So I should just use end. That gives me the last one. Right? And now I want to do that for each trajectory in my data set, right? So how do I do that? So I could either do, so I'm going to do an array comprehension again. So I'm going to do sort of traj n. And I'm going to iterate through this vector, which is called walkers, right? Yeah. Right. So for each thing in walkers, call that thing traj, and then take the end element of traj. Since traj are going to be vectors, that will give me the last element of each vector that lives inside this vector of vectors. And that gives me the correct answer. Right? So that's an easy way of extracting some number element, right? So for example, if I call I 10, I can also get the 10th element of each vector in that vector of vectors by traj number I for Trajan walkers. So this is iterating through vector walkers, the vector of vectors, right? So through walkers, which is a vector of vectors. We use these backticks to signal if you're in a markdown cell, what do backticks do? They do the following. This, if I put backticks and I put x equals 3, it will think of that x equals 3 as a piece of code and it will put it in a nice, or actually not that nice computer font, whereas it uses a much nicer font for non-computer code. So this is a proportional font, and the code is usually in a fixed width font. Okay, so that's one way that you could extract this data. So you might be thinking, well, this is ridiculous. Why didn't we just make it a matrix in the first place? And the answer to that is I do not have an easy way of making a matrix because I have this function that returns vectors, right? And so I would have to call this function and then like pre-generate some matrix of the right size and then copy the data from my vector into the matrix. So you could make a version of this function that took in the matrix and put this data in the right place in the matrix. That would be a solution. But so there's actually, now that I have this vector of vectors, I can use these array comprehensions. That's not so bad. Or what I could do is actually convert this vector of vectors into a matrix. How do I do that? So you have to decide, are these vectors going to be the rows of the matrix or the columns of the matrix? So normally we would think of vectors as column vectors. And so we want to think of them as the columns of the matrix, right? And then, so what I want to do, I want to take these vectors and stick them together so that they form the columns of a matrix. So we're going to concatenate them, which means stick them together in a horizontal way. And so we need the function hcat. So I'm going to put hcat of walkers, and you need to put ... here. So what that does, okay, so let's just stick two of those together. So hcat of walkers 1 and walkers 2. What is that going to do? It will take the walkers 1 as the first row, right? It starts 0, 1, sorry, the first vector in this collection. It starts 0, 1, 2, 1, 0, 0, 1, 2, 1, 0 going down. So it is thinking of them as column vectors. That's because I'm horizontally concatenating. This is the second column, and I stuck them together, and now I get an array with 2 dimensions, which has integers inside. So this is a matrix. It's a 21 by 2 matrix. It has 21 rows and 2 columns. Right? The number of rows always comes first. So now, how do I stick them all together? Well, I have to do hcat of walkers 1 and walkers 2 and walkers 3. And of course, this is ridiculous to have to write all this out. There must be a better solution. So you might think that it's just hcat of walkers, but unfortunately, that does not give me the right thing. Wrong. That just gave me back the same array, except that it turned them into, each of them became a matrix instead of, this is well, there's some complicated. It's like it became a matrix of vectors instead of a vector of vectors. It's not what I wanted. So what you actually need is walkers ... So what the ... does is called a splat. If you're used to some other language, it might be a star, Python. So I'm trying not to mention other languages, but just in case you're coming from, it's the same as star in Python. So what does that do? It says use each element of this collection as one argument to this function. And so walkers, we know, is a 10-element thing. It has 10 vectors inside. So this is equivalent. The splat is equivalent to is what I just wrote, right? So equivalent to hcat of walkers 1, etc., up to walkers 10, and you actually have to write them all out by hand, which is ridiculous. So instead of writing them out by hand, you do this ... and it will use them as if you wrote them out by hand. And when we do that, we get indeed a 21 by 10 array matrix. right? Array with 2 dimensions as a matrix is the same thing. Okay, so that's one way of doing it. A better way to do it is actually to use this form, reduce hcat, more walkers. That's faster, more efficient when you have a lot of vectors. Okay, so that's the correct solution, reduce hcat walkers. So what does that mean? It just means keep on hcatting walkers, one by one until you run out of any more to hcat. That's what the reduce means. So this is a higher order function. Julia is very good for this kind of functional programming, if you like, which just means, well, hcat is a function and I'm passing it as an argument to another function. And this is a very difficult thing to do in many languages, but in Julia, it's very easy to do and it's efficient, and it's very common to do this kind of thing. Okay, so now that I have it as a matrix, let's call it something. Let's call Walker's matrix equals that. Now I can easily extract the last column, right? How do I do that? Suggestions in the chat. Yeah, I really can't see any of the, oh, there it is. It was hidden. It's not very clever. Walker's matrix. Are there any suggestions? I can't see that. Okay.
Do you not see the chat?
Okay, now I see it. Walker's matrix colon end. Yeah. So if I want, the last element of the first row, I would do this, right? 1 is always indexing by row and then column. So 1 end gives me the last element of the first row, and then 1 colon 2 gives me the last element of the first and second rows, and 1 to end, comma end will give me all of them, all of the rows, and then I can, so that's the last element of all rows. And Walker's matrix, so I can abbreviate that as just a single colon, and then it'll take the first to the last element. Okay. Let's call that final positions, and now we can actually use that data, right? So it was kind of hard work to get there, but aren't the data stored as columns though, not rows? So why not just Walker's matrix end? So Walker's matrix end, so the way Julia works is that if you index just with one single thing into a matrix, it regards this index as a linear index that goes from the entry to the end entry one by one by columns. So you can't do that. You have to do the double indexing. Yeah, so that's different from some other languages. Okay, so now we have this data. We can look at what is the, where are the walkers at the last time step. So the data, I called it final positions. What am I going to do with it? What's the first thing I want to do with it? I just want to plot it to see where it is, right? So let's scatter that. Those are the final positions. Probably I don't have enough walkers. Let's get some more walkers. Let's just copy that data. Yeah, so I should have made this into a function, right? You don't want to be scanning back trying to find where your data generation was. I should have made this into a function. But anyway, walkers trajectory end. So I'm going to make 1,000 walkers. Let's say 100 walkers. And now I'm going to take the last element of each of them again. So traj end. This is n equals 20. Traj end for n equals for traj in walkers. And that's going to be final positions. And now I'm going to scatter that, and I'm just going to put a semicolon to hide the output. And then I'm going to scatter those final positions. We see something like that. So there's still not that much data. So let's do 1,000 walkers. Now suddenly we get a picture more like what we were getting last time. So this is, starting to look like, give me some information. It looks like there are a lot more walkers in around 0 than there are around 12, as we would expect, right? And indeed, there are none that are even close to 20. And so what do we need to do? We need to use the function that we wrote last time to count how many walkers are in different places, except that now the walkers can have different values. Zero, they can be negative as well as positive. And so maybe my approach of using a vector last time was not very satisfactory. So what I can do is use a package called statsbase that you do have to install. That has a function countMap. That is the function that you're going to write actually yourself, not using this, of course, but doing it by hand, using a dictionary. We're going to write that in problem set 1. But for now, let's just use the one that's in this package. Statsbase, base has a capital B. Packages are called base when they're like base, fundamental to some area. So this is a statistics base package. And Julia itself has a base package, which is sort of all of the standard under normal definitions of plus and things like that. I think that's right. Okay, so count map of final positions is going to give me some dictionary. So reminder that a dictionary maps a key to a value. This is exactly the dictionary that you're going to produce in problem set 1. And so I see that 10 occurred in my data set 18 times, minus 6 occurred 73 times. Okay, so this is let's call it counts. And now I can actually just scatter that object. So in the problem set, I asked you to extract from here the keys, these values, and the values, and order them correctly. But if I just scatter them, then it will actually draw this thing for me. And so we start to see something interesting, which is where these walkers are at time t. So let's bump this up to 50 and bump this up to 10,000. Now, even though I'm doing quite a lot of, let's say 100, doing quite a lot of calculations, this is just runs immediately because computers are fast these days and because Julia is taking advantage of the speed of the computer. But if you do this in other languages, running these simulations is actually like one of the slowest things you can do in many languages, at least the way we wrote it with for loops. Okay, and then, so I have final positions, and then I have counts equals count map of final positions, and then I scatter counts, and we get something, because the point is, okay, now I want to join them up with lines, but if I try plot of counts, and a dictionary does not store things in order. And so this dictionary is returning things in a random or sort of arbitrary order. And so now I can't just plot it using lines because it's trying to join them up in the order that they appear rather than in some sorted order. So I actually need to sort the data if I want to plot them like this. So we'll just stick with scatter for now. So what distribution? So what are we seeing here? We're seeing the number of walkers at position. This is on the x-axis, it's the position, and on the y-axis, it's how many of my 10,000 walkers were at that point. And so, so let's see, scatter of counts, comma, So what we're going to do is divide this by the number of walkers, right? So num walkers equals 10,000, and I can actually separate this with an underscore in Julia. Call this num walkers. And so now I want to scatter counts. I want to divide that element by num walkers. Now I get a probability distribution, except that it didn't work. Oh dear. Yeah, okay, so this is why we need to extract the data into vectors, because I can't actually do the operations that I want to do. But if we could divide this by the number, we would see that this is now a probability distribution. You can think of it as, okay, I have two alternative points of view. I can think of it as an ensemble of a cloud of 10,000 walkers all moving at once, or I can think of it as running the simulation 10,000 times, one after another, that are independent. And I'm saying, what is the probability that there's one random walker after 100 steps is at position 40? And the answer is it's very small. And this distribution, you probably recognize, is close to a Gaussian distribution or normal distribution. And that occurs, just really frequently whenever you have the same thing that we have here, which is that we're accumulating a collection of small influences. We're adding them up, and then we usually get a normal distribution when we do that. Okay, so the time's run out. So we didn't get to talk about what the mean of this distribution is or the width of it, but I think we covered some useful things. So I hope you are enjoying the course so far. Do give us feedback about anything that Alan just sent out a poll about what emphasis you would prefer in the course, although most people who are enrolled in the course are not actually on the call, so we should probably
a lot of people are watching the recordings, but it's really great to have you live. Right. It's so much more fun for you and for us.
Over Piazza, actually.
I suppose that's probably
what people like, but you have the advantage that if you're on the call, then you get to vote. Okay.
Yeah, I think those folks deserve an advantage.
Yeah.
Maybe, I don't know.
Okay, so so get to work on problem set 2. Hope you finished problem set 1. I hope you enjoyed it, and that you can now analyze the data. You now can access the data and analyze it whichever way you want instead of whichever way somebody else wants, right? That's the point. Or you can check if what they said was true, or you can play around what happens if you do this and this, right? You now have some tools to do that. Okay, thanks a lot. So we'll meet again on Monday.
All right, see you then.